As someone who has enjoyed science, color has fascinated me for a long time. You can think about color in many ways. There's a physics aspect to color, chemistry, and biology aspect to color. So I'll start with this statement. Humans perceive yellow when they see light with a certain wavelength. And I see that kind of as having three parts. There's a physics part to it. There's a biology part, a chemistry part to it, and a bit of biology here. So let me jump into this physics part. What does it mean to have a wavelength? So think of a wave. A wave is just a variation of a point in space. So here's the animation. Let's just focus on this little point here on this slide here. And just look at this red arrow. This red arrow goes up, and then it goes down. And then it goes up, and then it goes down. This property, this E property at this point in space is varying as time progresses. Sometimes it's up, sometimes it's down. And it's varying because something is passing through it. Something starts over here, moves from this side to this side, and as it moves through, it varies the property of this red arrow at that point there. If we pause it in time, we have this wave right here, and we say, hey, there's a top of a wave here, top of a wave here. That's a wavelength. So you can measure how long a wave is by looking from top to top. Now for light, it's an incredibly tiny number. It's about 500 billionths of a meter, so it's an incredibly tiny number, but it's just some number. It's just a gap between top points in this oscillation of this red stuff. So the physics there, a wavelength is just some gap between arrows in some sense. The chemistry, the biochemistry, it involves the eye, of course. And here's a little eye cross section. So some light comes in through the pupil, and it hits the back of the eye. And there's some neat cells in the back of the eye called cone cells. And there's a molecule in there that actually changes orientation when it's hit by light. So this is a chemical process induced by a wave that causes it to change orientation, that causes it to flip. So that's all I'm going to say about the chemistry, but there's some neat chemistry in there. The details aren't overly important, but it's pretty neat stuff. If you're into organic chemistry, take a look at it. So back to our statement then, the chemistry here is just something about some fancy molecule changing its orientation when it's hit by light. When that happens, there's then a cascade that happens in the back of the retina, telling your brain, hey, there's light hitting my cone. Now, the biology here is also exciting because at the back of the eye there's actually three different types of cones, three different types of cells that respond when a wavelength of light hits it. And these three types of cone cells respond differently to different types of light. Let's just take two. Take type A and type B. And if type A and type B are both hit by the same type of light, the same wavelength of light, the same variation of light over time, then maybe only one of these cones actually says, hey, brain, I see something. Well, different types of cones, a different wavelength of light, then a different cone cell says, yes, hey, brain, I've seen something. And we have three types, and about 50 years ago, we actually mapped out the sensitivity of each cone against the wavelength of light that's hitting those cones. So down here I have different colors of light, different wavelengths of light, different distances between those spikes of variation. And here we have how sensitive the cone is. How likely is that cone to send a signal to your brain? So here's one cone. If blue light hits it, signals go to your brain immediately. Red light or orange light or yellow light, nothing really happens. So we have a blue cone. We have a cone that works really well in green-yellow light, and a cone that works well in kind of yellow to red light. So we have different cones that detect light differently. The blue cone doesn't fire at all when red light hits it. And this green cone fires best in kind of the yellow-green area. And the red cone's only when it's firing in the deep red area. And engineers have used this to trick our eyes for a long time. We actually have televisions and your phone screens and your LCD screens all use this property to make you see a whole bunch of light. So over here, I have an iPad, and okay. So I have a USB microscope and an iPad here. So attached to this is a microscope that just zooms in on the screen, and I have the USB microscope on the iPad. And right now the iPad has a black picture, so we're seeing nothing. But I'll drag this over and turn the camera on. So this is zoomed in. This is a kind of a live picture. I can move the microscope around. This is a live picture of what it means to have blue light coming off the screen. So there's a blue subpixel on the screen that activates our blue cone cell, so our brains perceive blue light. If I change the color of the iPad to red, well, no surprise, there's a red subpixel. So the red subpixel gives off red light, and we see when we perceive red light. What's really cool, though, is if I make the iPad screen white. If I make the iPad screen white, this is what's happening on a very zoomed-in scale. There's no white light coming out of this iPad screen. When you look at your phone and you see a white background, there's no white light entering your eye. There's only these three colors. There's red, green, and blue. But because we have those three cones, and we have these three colors make all three of our cones fire, our brain perceives red, green, and blue light as white light. So no LCD, no TV ever gives off white light. They've only ever given off red, green, and blue, but our brains see it as white. I also love yellow. Here's yellow. Yellow is actually green and red. So yellow light from a screen is not the same as yellow light from a banana, from a lemon, or from my tie. So my tie and the iPad screen, you can't see very well, both look yellow. Look at yellow on your screen. It looks yellow, look at this yellow. But they're different yellows. This yellow really is the 560 nanometer yellow. It's really yellow light. But yellow from a screen is not yellow. It's only got red and green in there. But our brains are tricked. If our brains receive these two colors of light, our brain thinks, hey, that's what happens when I perceive yellow light. So the yellow light from nature causes both of these cones to fire. Engineers have designed these things to make those same cones fire, and we see this as being yellow on a screen. So yellow is not a real color on a LCD or on a phone. Other cool color, here's our rainbow again, is magenta. You don't find magenta in the rainbow. Roy G. Biv, there's no magenta there. And you might say, well, magenta is just purple, but it's not. Like, this color of magenta is not this color, it's different. So magenta is actually happens when your screens create these two pixels being illuminated. It's illuminating the two ends of the spectrum. It's when we see blue light and when we see red light, our brain mixes those and makes up a new color. This is not a real thing, not in nature. This color only exists in our minds. In many senses, it's not real. Without humans, without animals to perceive green, red, no, blue, and red, magenta doesn't exist. Magenta has no wavelength. It only exists in our brains when our red cones and blue cones fire. So I'll leave you with this. This is also true for every other color. All these colors we see, this beautiful yellow, nice greens here, those are all just perceptions that are happening in our brain when certain wavelengths of light hit our cones. They aren't real in the sense that this yellow feeling is a real thing. This is purely existing as a feeling. We feel yellow, we feel red, we feel magenta. Because when real light hits our eyes, our brains interpret that as some color. Thanks.